Good morning, mathematicians. I skipped a day. You can't put me in a box. You can't figure me out. I'm too mysterious like that. I gotta make some more real videos at some point. I skipped a day. But when? That's the question. Okay, where were we? We were talking about D-modules and stuff. That's what we were talking about. Yeah. You're reading The Republic of Plato. Nice. Yeah. I read The Republic back in my first year in university. Took an intro philosophy course. Yeah, it was pretty dope. I liked it. I liked it a lot. I liked discussing it in class. Yeah, how many books have that much staying power over the years? Republic has held up. Okay, so last time we finished computing an equivalence going from from local systems to representations of the fundamental group. We computed an example of that. Now we're going to need to compute. Well, where am I going? Let's talk about D-modules. So we had local systems. Those were in correspondence with the representations of the fundamental group. And then also we saw that these local systems could arise as taking the kernel of a connection where M is a quasi-coherent sheaf and nabla is a connection. If you like math, it's very likely you like philosophy too. I suppose so. Well, I don't know. I think it depends. On the mathematician. Like, I think it depends on the kind of math you like, right? Like, I would venture to guess that, well, yeah, I mean, maybe in general you're still more interested in philosophy, more likely to be interested in philosophy than the general public, but I don't know. I feel like some people are mathematicians because they want to understand the real world and they want to cut through fancy mumbo jumbo and just slice to the heart of the matter and you know, peel away the extraneous details and just get to the practical thing. So I suppose you could say that, you know, maybe there'd be utilitarians philosophically. So I don't know, maybe I'm defeating my own argument. Yeah. Whereas, I don't know, if you're doing more abstract kind of math just for the sake of math, well then maybe you're also the kind of person that's more into just like contemplating the nature of consciousness or something. So maybe either way you're into philosophy, I don't know, but yeah. Yeah, so the next thing to talk about then is how this relates to the concept of a D-module. So a D-module, we've got some complex algebraic variety. And we'll let dx be the sheaf of differential operators. So basically, that is the sheaf generated by the structure sheaf and the sheaf of differentials modulo the Leibniz rule. Well, basically you just have sheaf of derivations. You just have, I guess I don't even really need to write this because you're having the derivations act on OX in the usual way. So, for example, if we're working with just affine, complex affine space, the global sections of this is going to be the ring in n polynomial variables, but then also we're going to attach these n partial derivatives with respect to each variable. And then, here we have the quotient where I want the Leibniz rule to hold. Well, so for I and j not equal, these should commute. And same thing here. Oh, hello, Julie. Hello. Talking about the definition of D-modules and connecting it to the things that other things I was talking about recently. And then finally, of course, if we imagined we had, if these were the same, and we imagined we had some like arbitrary polynomial here, well, we would use the Leibniz rule to conclude to get f plus xi dif. So just isolating out the variables, we should then have the relation which we could write, oh, hello, Argia. Thanks for tuning in. So we could write this relation like this, or even if you wanted to make it really compact in commutator bracket notation, we would write something like this. So, Duck with a Monocle just wanted to ask if I've ever used full page in OneNote. Yeah, like, yeah, I guess that's, I guess that looks nicer. Yeah. Yeah, so that's the say global sections of this sheaf. And now a dx module is a quasi-coherent sheaf. M which is a dx module. I mean, yeah, what do I mean? I mean, what I mean is like it's a sheaf of modules over this sheaf of rings. Yeah, I suppose. I mean, I guess in a sense you could say it's. Well, yeah, I don't know how deeply quantum mechanics it is. I mean, yeah, of course you're looking at the commutator relation, and of course quantum mechanics can also be phrased in terms of the failure of the derivative and multiplication by a variable to commute. It's definitely true. And you can definitely, in some of the geometry I do, there's definitely like ways that it interacts with quantum mechanics. But also, I think maybe in this general context, it's just a specific. I don't know. Maybe more coincidental, or maybe they're both. I don't know, aspects of it of a very general theme. You choose to move the toolbar down, and it seems to always end up in what you've written. Oh, I'm not gonna mess with the toolbar. I like it where it is. I am not a physics researcher. I am a Ph.D. student at the end of my Ph.D. in mathematics. I know a little physics, just, I've taken some courses here and there, and I pick up some things as I go. But I'm ultimately a math student. But I think I'm going to let you guys entertain yourselves for 30 seconds while I grab some more water. Yeah, exactly. Stay hydrated, stay caffeinated. Yeah. Okay. So, how do we? Well, what are some examples of this? Well, dx, of course, is a D-module over itself. And so similarly, if you take any, I guess, for any left ideals, that's really a sheaf of ideals. For any left ideals, maybe I should write it this way. This will be a D-module. And so, in fact, we actually get many important examples this way. So, two very important examples is, so say we're looking at the D modules just over the complex numbers, the D module and the complex numbers, then we look at let's take the, of course, we could take the D module, which is the quotient by x, and we'll look at the global sections of this, and that's basically just C adjoin delta, or C adjoin del, and as if we do the opposite, of course, we just end up getting this polynomial ring. These will both be really important examples for us in a moment. What do I plan on doing after I'm done with the PhD course? I don't know. I'll apply to postdocs this fall, but I also kind of want to make some money. So I want to not be poor, and I have student loans to pay off. So I don't know, I might go look for a real job as well. I don't know what I'm going to do. I guess I'll learn to code. Or who knows, maybe I'll end up just taking postdocs and staying in academia. I don't know. We'll see who wants me more. More of a literature than a philosophy guy. So I will counter with recommending Günter Grass. Gunter Grass tin drum. Well, Lola, it's not guaranteed I'm jumping to industry, but I mean, I don't know. I do think about it a lot. I've been poor my whole life, and I'm tired of it. I'm getting old, and I just want to have certain things, and I want a certain amount of security, and having money would offer me some of those things, and yeah, having some math skills, I feel like puts me in a position to make some decent money. So, yeah. Yeah, I don't know. There's also lots of things I think about in industry. I'm like, God, I'm not going to enjoy that. Yeah, I don't know. I don't know what the right move is. YOLO into Bitcoin and retire in 10 years. Am I right? Yeah. So, but now, I mean, the definition of a D module is pretty close in many ways to a quasi-coherent sheaf with a connection. In fact, I mean, if you had a quasi-coherent sheaf with a connection, it already is by definition an OX module. So to promote it to a D module, one would just need to also equip it with an action of the differentials. But how could, or the derivations, whatever, potato Picasso. So how could you do that? How could you define that in a consistent way? Well, supposing you had some derivation on M, well, remember that a connection is a morphism from here to here, right? So if you apply your connection to little m, this then basically becomes a thing that eats derivations. Well, technically you've tensored with that, but what I mean is, like, if alpha is a one form and f is something in your sheaf M, retirement. Now we're reenacting the way Gawa died. Is that how I'm gonna go out? Maybe. Who wants to fight me? So we can just extend this, right? So if we plugged in a derivation, then so we can just plug this in, and like alpha v is now going to be something in OX, so that can act on F, right? So that's exactly what we do, is we simply take take nabla, plug in M, and then evaluate at V, where evaluation means this. And then that recovers an element of M. So that defines an action. So we also sometimes, as a shorthand, write this as nabla sub V acting on M. Because also, like, this is also like a directional derivative. This is like the directional, this is like the derivative of M in the direction of V. Now there's one thing that we need here. I guess it just comes in to just make sure that you get like compatible actions somewhere in the modular axioms. I never went through and did the computation myself. But in order to get a D module, apparently what we need is a flat connection. So it turns out in general, it is not the case that if you, for any pair of vectors, it is not the case that if you apply them two in a row, that it will result in the Lie bracket of these. Basically, the curvature. So the curvature, what's the notation? I already used notation that I normally use. Maybe I'll just call it, I don't know what to call it. But the curvature is basically, so this is not true in general. The curvature is the operator given by this. And we say that a connection is flat if it has zero curvature. By the way, something I didn't mention before is that if you have a connection, for any connection, you can always find... well, I've never actually used this notation. I mean, this is common... Yeah, I don't know. Yeah, maybe it's curvature. I don't know. I mean, in texts that I've used, sometimes I've seen like little theta is used for the matrix of the connection, and big theta is used for the matrix of the curvature. But I already used that. I've also seen like big omega used for the curvature and little omega for the connection, but I've already used those in the above. So. Yeah, I don't know. But so we can always choose local coordinates such that the connection is given by the exterior derivative plus multiplication by some matrix of one forms. And you can go ahead and check that that is that's a connection. Well, rather, if you have a okay, whatever. There's a theorem that says you can do this. So locally, we can always choose a coordinate patch that looks like that. If you choose such a patch, well, sometimes also the curvature is just written as del squared, because it's basically just applying del twice. Or nabla. I call it del, but it's nabla. And if you manage to find local coordinates such that this is true, then the curvature will locally be given by, what is it? I think it's dA plus d wedge A with itself. So by this I mean you component-wise, right? The entries of A are one forms. So you just component-wise take the exterior derivative of each of those. And then... by A wedge A, I just mean ordinary matrix multiplication. However, when you multiply the entries together, you're multiplying them via the wedge product. Yeah, so that's connection and curvature. And so, I mean, another way to check that your connection is flat is basically like this matrix will be 0. Yeah, so the point is if you have quasi-coherent sheaf with a connection, you can upgrade it to a D module using that connection. And in fact, this process is reversible as well. So that is, if you have a D module, then you can define a flat connection on the underlying quasi-coherent sheaf. Well, how is that? I mean, basically this thing has a local frame, right? Given by, you can choose open sets with some basis of the coordinate derivatives. And so you can imagine, so we said that if you have a connection, right, you can take the directional derivative of each element. So probably, hopefully it's maybe not too hard to imagine that if you, this will be linear in this component, right? So if you simply define what this should be for all I, then that should define for you a connection. And indeed, that is the case. And so if M was a D module, right? So again, that means it's a quasi-coherent OX module. And then how do we define a connection on it? Well, because it's a D module, it comes equipped with an action of these things. And so what are we going to define the value of this connection to be? Well, we just define it to be del I acting on M. Interesting. What fails if the connection isn't flat? You're going to try working through that. Yeah, maybe we'll look at some things. Maybe we should compute that together. Yeah, I'm guessing that it's just I'm guessing that it's something to do with the module compatibility, right? Like if you have a D module, it has to be a module first and foremost, right? So if you had two things, I don't know, alpha beta acting on M, my guess is that this is probably where it fails. You need this to be the case, right? And so, well, maybe we could try. Maybe we could try unpacking that, right? So this would be, I don't know, maybe let me call it U and V. So UV acting on M should be U dot V, U dot V dot M. But what is this? So this is nabla UV acting on M, which is nabla U of nabla V of M. Yeah, this has to be it, right? This has to be it. What's K-theory? Good question. I get that a lot on this channel because of the name. Yeah, probably long-time viewers are tired of hearing me say this, but actually I don't really work in K-theory. It's just because my name starts with a K. I thought it'd be a good name. Basically, K-theory is a cohomology theory of sorts. So it's just some invariant that you can apply. So you have some space, like a scheme or a manifold or something. And then you can, the K rings, you get a bunch of rings. These are just sort of invariants. So it helps you tell your spaces apart, right? So if X and Y were isomorphic to each other, then all of their K rings would have to be isomorphic to each other, for example. Ooh. That's a basic idea. For any abelian category, if that word means anything to you, examples include vector spaces, the category of vector spaces over a given field, or the category of abelian groups, or the category of modules. In those cases, the K-naught ring of an abelian category is basically... okay, it's more complicated than what I'm about to say, but you can basically think of it as being like the free abelian group generated on the simple objects. So, for example, the K-naught ring of vector spaces is isomorphic to the ring of integers, basically because you have every finite dimensional vector space is completely determined by its dimension, which is a natural number. But then, you're like groupifying things. So you basically add formal inverses to each of these. Yeah. But then, things get a little more complicated. There's also algebraic K-theory and topological K-theory where things seem to differ a bit. Grothendieck's weird definition of differential operators in terms of commutators. I'm not sure I'm familiar. Yeah, the higher K groups are complicated. Those seem to be defined in terms of maybe we should go to specific pages. But in other cases, I've seen the K groups defined as like, the K group of some category is like, it's like you take the ith homotopy group of the nerve of the category or something like that. Crazy stuff. You just started learning algebraic topology, and YouTube... Oh, message disappeared. Yeah, I don't know, Arad, this differential operator thing you're talking about. If you can point to where it shows up. You just started learning algebraic topology, YouTube algorithm. Thought it'd be a good idea to recommend your channel. Wow. Hopefully it does turn out to be a good idea. There's maybe some things on this channel that you might find interesting. Maybe my videos on homotopy type theory, possibly. Also, a million years ago, I did promise some people to compute some fundamental groups in my live stream, and I never really did that. Oopsie. Okay. Oh, yeah, this is the equivariant K-theory. Yeah, that's even more complicated. Topological K-theory is easier, I think. I can look up Grothendieck definition, differential operators. Okay, let me look it up. Abstract algebra. Oh, that's... here we go. Differential operators on a module over a commutative, associative, unital algebra over a field of characteristic 0. Um, degree zero operators are endomorphisms of M. That makes sense. Given F, denote F hat, the operator of multiplication by F. Sure. A linear map is called a differential operator of degree at most D. Hello, Rahul. Hello. Okay, this kind of makes sense, right? It's degree at most D. Degree at most D. So D is degree at most D if df is degree at most D minus 1. I mean, let's see. Should this recover the original thing? Not the Tom spectrum of the orthogonal group. Okay, well, yeah, I would hope not. We were talking about some nonsense with D-modules. I was talking about the equivalence of D-modules, but now we're on a tangent about K-theory and differential operators. So, I mean, let's just try and square this away with our ordinary thing, right? So certainly, like, if we just think about polynomials in one variable and let del be the derivative with respect to that one variable, we should think that this is degree at most 1, right? So, I mean, for all polynomials, f, the commutator is what? It's, well, I mean, basically, as we saw above by the Leibniz rule, this should just be 1, right? This becomes del f minus f del, but del f as an operator is del f plus multiplication by del f plus multiplication by f del minus f del. So I guess those terms cancel out. Oh yeah, and then this is right, and then this is just multiplication by this function, and that's definitely degree 0. So this definitely lines up. Devil Sam the Gamer just came. Can you tell me my job? Well, I'm a Ph.D. student, so my job is kind of to do research in mathematics, although I would say probably very little of my, that's what I like to tell myself, but very little of my stipend comes directly from that. You know, most of the money that feeds me every day realistically just comes from TAing, you know, marking, grading papers, stuff like that, giving tutorial lectures. So, yeah. But I like to call myself a mathematician anyways. So, I mean, I don't know. This definitely makes sense to me. And then I'm like, if we plug this in, with like del squared, yeah, I'm sure we find it ends up being the same as a degree 1 operator. But in general, the relationships between differentials and commutativity, or lack thereof, is fascinating. Yeah. The algebras and Hochschild homology, even. Interesting. Yeah. Yeah. Yeah, this should on the list of people talk about e to the I pi, whatever their favorite equations. Probably this should be up there actually. This is like this is everything, right? This is calculus. This is differential geometry. This is D-modules in algebraic geometry. It's quantum mechanics. I mean, this is actually of fundamental importance. Anyways, I should probably get back to work on my thesis. Or screwing around doing other stuff. Yeah, thanks for joining me. You've waited 4,000 years for this? Cars? Is this a quote from like Warhammer or something? Well, it's good to see you again, New Wave Infantry, even though you got in right at the point where I said I was signing off. But I'll see you again soon. I'll probably be back like tomorrow or something. I'm going to go prove some stuff. You should go prove some